Okay, this is my solution for the problem that we did on Friday of week 8. And we were talking about a coil of wire as an inductor. And so we had a coil of wire in the storeroom, and it had a total of 1,000 turns of wire. It had a length of 0.10 meters and a diameter of 0.06 meters. So it was about 10 centimeters long and about 6 centimeters across. Okay, and our challenge was to find the inductance L. And so the inductance L is defined such that the EMF across an inductor, the voltage across an inductor, is equal to L di dt. And so what we did was we started by just putting a current across the inductor. A current through the coil. And I know that something's going to be induced because I know that there is a magnetic flux if there's current through the coil. So if we start with some current through the coil I, well, let's see. That means that there's a magnetic field caused by that current times the area of the coil. And so the magnetic field, I'm going to get that from Ampere's law. So I'm going to make my coils here. And I'm going to do a quick Ampere's law that if I have a total of n turns divided by the total length, then, and I apply Ampere's law, I'm going to get B at dl around that loop. And all that's really going to matter here is the length. And so that's going to be the current through the loop times mu naught. And so if I just do it over the whole length of the solenoid, I get B times the length of the solenoid is the total number of turns times the current. That's how many wires are poking through my lasso, times mu naught. And so B is N over the length. Now I should have written length here. I'll fix that. E, because we're using L for inductance. So it's N over length times I times mu naught. So now I'm going to ask the question, what happens if I actually change the current? Oh, I forgot to write up here that the area of this loop is pi times the diameter divided by 2 squared. Okay, oh, and the total flux here is the total number of turns times B times A. Okay, so now I'm going to change the current, and I get that I start with the flux here is N times B, which is N over length, times I times mu naught times pi times diameter over 2 squared. And so if I change the current, I want a d flux dt. And I take a look at this and I realize that the only thing that can possibly change about this flux is that current itself. And so I'm going to write everything out front. N squared all over length times mu naught times pi times diameter over 2 squared. And the only thing that can change here is current. So I'm going to use Faraday's law. And I'm going to use Faraday's law that the induced EMF is equal to the rate of change of that flux. So that means that this EMF is that voltage drop across the inductor. Okay, so that means that I'll write delta V is equal to, and I'll just copy what I have from down there, m squared all over length, mu naught, pi, diameter, over 2 squared, vi dt. And so I look back here at the definition of what L means, and it means that this whole thing right here must be the inductance. So if I plug all these numbers in to Google Calculator, 1,000 squared times, and it calls it, I called it the permeability of free space. Google actually calls this the magnetic constant, which I've never really heard before, but that's okay. Times pi times 0.03 meters squared divided by 0.1 meters. You should actually try this and see what you get. And what you'll find is that the answer comes out, gotta love Google, in Henry's, 0.036 Henrys, or 36 millihenries. Okay, that's it.